Hello everyone. This is section 6.5 unsymmetric bending. In this section, we'd like to study some special cases for bending. We call it unsymmetric bending. What's the meaning of unsymmetric bending? Usually it means two cases. First is your cross-section is not symmetric, or the other case is your bending moment is not along or perpendicular to your symmetric axis. So based on the above statements, these two important assumption or requirement we mentioned in probably at the beginning of this chapter or in the previous two sections, I think, where we derive our flexural formula. These two statements, these two requirements may not be necessary anymore, especially when we learn the skill in this section. We will know that these requirements are not necessary for all the cases. So let's go to see how to learn or how to know these special skills. Here's the case. As can be seen, this one. The upper part and lower part are not symmetric. Of course, you still can see the so-called symmetric axis along along y-axis here, and the neutral axis here. So basically, this example, we still can use we still follow the basic requirement we mentioned before. So you can say that this is a very basic or first level unsymmetric cross-section. It's just unsymmetric for the upper and the lower part of the cross-section. So how to deal with these problems? First of all, we need to follow these two processes. First one is try to find the centroid first, because this structure, you really don't know what's the centroid along the y-axis. You know it may not be at the center, but you just don't know where. The second part is, once you determine your centroid and the corresponding neutral axis, then you can apply your flexural formula into this structure, into this cross-section, and then you obtain your bending stress. So let's see how to determine centroid first. This is the equation we derived first, YdA integration along across the cross-section A. And in practical cases, for a T structure like this shape, if you don't know where the centroid is, you just determine our original of this cross-section from just like this place or somewhere else. Doesn't matter. You can start from arbitrary location. Usually we select the bottom plate surface or the top surface. Some guys may select the middle surface. Doesn't matter. You just select one point. For example, in this case, we determine this place. The bottom surface over here is our original. Then we'd like to determine our YdA integration for two parts. The upper horizontal beam and the middle is the vertical beam. These two portions, you can find the centroid of these two parts easily. For the vertical part, this is the centroid. And for the horizontal part of this beam is over here. And then the y-axis is called y1 bar and y2 bar. We substitute back to this place and multiply with its own area. Then after we summarize that, we can say that for total area A is the summation of these two areas times a known y bar where our centroid is. Then after that, our process can give us our y bar, the real value of y bar, where our neutral axis is located there. Our original is located as well. After that, we substitute these function, or we can use this function together with the corresponding I and Y into this structure and determine the correct structure bending stress for this moment M. And about I, it also should be very careful. For example, for each part of this beam, for example, the upper part and the lower part, these two parts actually, its own centroid is located over here and here. They all have certain distance. For example, this one, y1 prime bar and y2 prime bar, this one and this one is the distance from the original of the whole surface or whole cross section. So we need to add the contribution of this part over here. That's very important terms or component in these moment of inertial derivation process. Okay, so just remember that not their own the original I for each part you need to consider, but also need to consider the distance from its own centroid to the centroid of the whole surface, whole cross section. So the contribution of these two parts should be considered as well. Next one, we try to see one example and check if we learn this skill very well. This is like the N-shaped cross-section or so-called C-shape. But anyway, you can see that for this beam, we apply a point load, 2.6 kilonewton with an angle for this right angle is 5/12-13. It's a very typical or a special combination of these right triangle. For this case, we can divide or decompose these 2.6 into two parts. One is the vertical part is 2.4 kilonewton. The horizontal part would be 1 kilonewton. Apply at the end of these cantilever beam. Then we'd like to see the maximum bending stress at cross section AA. So check the free body diagram at AA. We got the shear force coming from 2.4 kilonewton. Horizontal force, or the actual force, we got 1.0 kilonewton. But notice that these point force apply on the surface, but our resultant force and moment located at the centroid of this cross section. So this is a very important contribution for actual bending moment from horizontal or the normal or the actual force. Of course, the bending moment should be considered as well. Okay, let's try to see where the centroid is. We mentioned for a long time in the previous slides. Where can we get this one? We divide these cross section into three parts, two vertical portion and one horizontal portion. Of course, we really don't know where the neutral axis is or the centroid is. This C point, we don't know where it is. So we just take one surface or one location as our temporary original. For this case, we probably start from, let me see, from from the top surface. That would be far more easy. This top surface, you can determine the distance of the centroid for the upper or the horizontal part would be 0.001. That would be one so-called white bar for this portion. And the other part for the centroid would be this 0.1. This is the distance from this point to the middle of the vertical portion. And we times 2 over here because we have two pieces. One piece is for horizontal one, two pieces for vertical one. Then the area of the vertical one would be here, and the area of the horizontal one would be here. Once we add all of them together, divided by the overall area, we get the 59.9 millimeter. That's the distance from this point to here, and this is called the Y bar. So that's our Y bar is, unfortunately, Usually, these types of questions, you usually have very weird number for your y bar. So be careful. In the following, all the derivation will be pretty ugly values, numbers for each result. Let's see what will happen over here. This is the result moment we really want to know. This is the one coming from shear force 2.4 times the arm would be 2 meters. This is one for actual force and with the gap from the top to the centroid. So that would be 0.05909 meter. And the result moment M is here, so you get 4.859 kilonewton dot M. That is why I said usually pretty ugly. And once we determine all the above things, we still need to figure out one important factor we call the moment of inertia I based on this equation. Try to remember this. It's very important. Of course, this will make our derivation of this equation pretty long. This is the one for horizontal one. Originally, this is the I with AD squared. This is the other I for vertical one, and this is 80 squared for that, and times 2 because of 2 pieces. This is the total number, total value of I. Once we determine centroid, we determine our moment of inertia, then we can apply that to our bending stress. That's the maximum one, 16.2 megapascal. And the top surface, we have a stress with 6.79 megapascal. Okay, so of course, this is from the bottom point. This is from the top point. And the maximum point will be the bottom one because we got the farthest distance over there. So that's all we have from this example. Here's another case. We got a rectangular beam just like this, very simple, but we'd like to see if we add 2 tiny ribs over there at the bottom, and if we have better performance. What's the maximum normal stress or the maximum bending stress in both cases? So in this case, we'd like to see if we add these strengthened structure, so-called ribs, on the bottom, can we derive better performance or not? Just try to compare these two results. First of all, this is the initial case. Pretty simple. No additional requirement. Just follow the very typical cases because we got symmetric along all the axes. So our I is here. We substitute into that. The maximum distance C is here. We get the stress with 4.44 megapascal. That's the maximum stress within this structure. Then we add one structure or 2 ribs at the bottom. Then after that, we'd like to see what we need to do. First of all, because we add 2 ribs at the bottom, so you probably know that you will face a unsymmetric structure for your upper and lower portion. So after that, we need to determine centroid again. This is the strategy. You can see that this distance is the upper portion, this is the distance for lower portion. Each of them is the centroid for each case. Okay, so let's see what we will have. We determine the upper surface. I think let's see. Okay, we use this as a original point. This distance is the centroid for upper part, half of the thickness, and this is for lower part. You add 1 thickness and half of the thickness of the rib. Okay, very tiny value for this one, and we times 2 because we have 2 pieces. After that, you get C as this value. Okay, this is the new centroid, and then we use these new centroid to determine our moment of inertia. The steps or the process, you need to follow this order. The order is very important. Find your centroid first, determine your moment of inertia, then substitute into your bending stress formula over the flexure formula over here, you get this value, 4.65. It's a surprising result. It says, oh my God, this is larger than what we expect here. So it means adding so-called ribs on the structure. It seems to strengthen that, but increase your normal stress much larger. You do not decrease that. So this reason calls, let us know that this strategy, you should neglect that. This is not a correct process or correct strategy to strengthen your structure. Otherwise, you will face a lot of challenge for this problem. Here's a so-called one advanced case for this problem. For advanced unsymmetric bending process, just like these illustration, you will see that you don't have a symmetric axis along any direction. It's just a random shape, right? Just like a potato, all right? So if you apply a moment M over here, your axis here, Z is the axis of the moment, and the perpendicular axis is Y. And then if you want to know how to deal with these kind of cross-section, we need some special skill in the following. First of all, try to review one important formula we call equilibrium formula. It's coming from the resultant force Fr. The actual force should be 0, resultant moment should be 0, resultant moment along the axis, where the moment m is, should be equal to m. That's three basic equation we have in this cross-section. We'd like to use that to determine what? Determine what we can have from them and determine what we need to do in the following. Okay, so let's start from the first equation. The first one, you will see that the summation of force, it means dF equals to sigma times dA. We summarize all these dF together into on the surface, and we should get 0 because we don't have any resultant force along this cross section or at the centroid. So after we substitute sigma equation into this integration, and then we remove all the constants c and sigma max in this integration, we only left yda equals 0. That's the equation. We know that it's coming from so-called centroid function. You can use this function to determine a correct centroid location. The next one, MRY, is the moment in along y-axis. Y-axis here, okay, should be 0. Okay, this is the moment perpendicular to the applied moment in our illustration in the figure. So how to deal with this equation? We try to use dF here, and for moment y, the bending arm should be z, this distance. So you get z sigma dA should be 0. After you integrate all the little dmz, dmy together. And then we still substitute this equation over there. So let's see what we do here. We substitute this. We also substitute this. And here. So that's the way we derive all these equations. Of course, we all need to take the c and sigma max away because they all equal to 0. They all belong to constant. They don't need to put into your integration. So after we process these, we deal with this process. After that, we get the zy dA. The integration of that should be 0. And what's the definition of this special integration we never learned before? It's called product inertia. And this equation actually is using to determine our principal axis. Okay, we have two. All right. After we determine all of these, the final equation actually we have learned that, or we have known that in previous section. This is the one to determine our moment of inertia I. Okay, so no matter the first one and second one, the first one or the third one, we have learned that in previous section, but this section we start to learn the second one. The second one will be important in the following. Here's the case to deal with cross-section with arbitrary cross-section, including symmetric or unsymmetric one. Of course, in symmetric one, you don't need to go through all these three steps. You only need the first one, or even you directly go to the third one. So let's see what's the complete or the general process. First of all, try to find your centroid based on these functions. Okay, you determine your C first, and the next principal axis find. How to find this? Use this equation to determine where or which direction of your axis can give you this integration equals 0. Usually, this process use so-called Mohr circle approach. For this kind of name, Mohr circle, actually we haven't learned that in these in the previous chapters, but we were going to learn that in chapter 9 and 10. So if you any senior students in this class, for example, you are third grade or fourth grade student, then you will know what the Mohr circle means, and this is very powerful for the for this kind of derivation. And then the third one would be our factor formula can be used based on the I and this formula. So this star note means for the product of the inertia, it will be 0 when your y and z are principal axis of the inertia. So it means if you set your y and z direction, you need to tilt in certain direction and find where our production so-called the principal axis of inertia would be 0. And if the axis have a symmetric axis, any symmetric axis can be if you have one, then your principal axis can be found easily because they are already these so-called principal axis are orientated along and perpendicular to your symmetric axis. So that means if you can find one, then the other one would be perpendicular to that, and both of them belong to so-called principal axis. So that's why I said if you have some simple cases, you can directly find their symmetric axis. Their centroid may not be found, but their principal axis can be determined immediately. So that's why you never use the second step before. If you have these arbitrary one, you need to go through 3. Okay, but in previous section, we just don't use that anymore. We just didn't use that, actually. So this is one example, or some examples we can use the above strategy. For this one is the C-shaped structure. It has symmetric axis along Z because the upper and lower part are symmetric, but it did not. This cross section does not have symmetric along the y-axis. The right and left one are not symmetric. Okay, so in this case, this one give us one principal axis. You just need to find the centroid over here, then determine the principal axis based on the symmetric axis here, and you get the other one over there. And then you can go through the following factor formula in the following. Okay, so this is the first equation. This is the second equation to find the principal axis. This is the one you can find your bending stress. How to deal with these Z-shape cross-section? Actually, the middle point, you can determine that as your centroid. That would be easier. However, your principal axis really cannot directly find by your eye, by your intuition. You need go through this process, product inertial, and derive the principal axis. Otherwise, there's no way to deal with that. We will see one example for this, actually. And here is another case, we call it the L-shape cross-section. Okay, this kind of L-shaped beam, the symmetric point would be the axis, 45 degree along the 45 degree. And this one give you another principal axis along y, perpendicular y. Then we still can neglect the part, but our centroid is a little bit painful because you don't have symmetric along any direction of that. You need to determine that one by one you need to go through this process once to determine y bar, and of course you need to go through another process we call z bar again. Then you will find the final result. That's another difficult cases we're going to see in the following. Here's one example to see how can we deal with this kind of unsymmetric cross-section for bending moment M, like this, 20 kilonewton dot M. Using the method we mentioned in Appendix A, we call it the Mohr circle method. The principal axis y and z are determined, just like this one, and the angle 32.9 have been derived directly for this problem, so you don't need to worry about that anymore. And the IY, IZ are given, so that will give our life much more easier. Otherwise, you need a lot of skill to figure them out. Finally, these problem asks us to determine our normal stress at point P and orientation of a neutral axis. These are the two important requirements of this problem. For the first one, we can use what we learned in the previous section, and you try to deal with that. Some of the skill we're going to discuss in the following. We just use these as an example to show how to deal with unsymmetric part. So if you don't know some of the equation in the solutions, don't worry about that. We're going to learn that in the following part of this section. Okay, so how to deal with this maximum point of moment of inertia first. It says the axis represents the principal axis for the maximum moment of inertia. So in this case, our moment m cannot directly be used in the derivation. We need to decompose that along the new axis z and y. This is the decomposition of the moment. Okay. After that, we need to determine what's the location of our p. Originally, it's minus 0.2 meter and 0.35 meter over here, based on the original axis y prime and z prime. Okay, this is the location of P. And this distance will be x-axis in minus direction, so it's minus 0.2 meter, and the height will be 350 millimeter or 0.35 meter. Okay, so that's the case for P. And then based on the color triangle, this is color triangle we'd like to see. You can use that to determine the axis, the coordinates of P in the new axis. Okay. This one. You need to know the distance of this one and the distance of this one. Okay. So you need to know these two distances for P. So how to deal with that? This is the result. You actually use this triangle to get this distance together with this one. You actually get the new YP in the new axis. This is the result for y-axis. You add this distance together with this one. You get minus 0.358. Okay, that's the distance for y in minus sign. And for the z direction, the z would be this distance minus this one. You get 0.1852 meter. All right. This is another one. After we determine both of them, we substitute into our bending stress function. Since we decompose that into two directions, so the moment for mz give one stress, the moment y give another stress, and based on the direction, one is minus sign, the other together with this minus, this actually is the positive sign. This is a positive sign together. We add these two together, we get the 3.76 megapascal. That is the total stress for sigma p. For the orientation of the neutral axis, we need this function, but the way we derive this one, you need to go through the following contents, and we're going to see where can find this function. This alpha can be derived based on this equation, and then we determine the new neutral axis over there. Notice that the location or the angle of neutral axis is not the same as our y-axis. They have a certain angle between them. Okay, about how to decompose or why we need to decompose our moment along the new principal axis, and where can we determine or how can we determine the so-called neutral axis direction. We can learn all the things in this portion. We call it moment arbitrary applied. So in this case, actually we select a very simple cross-section. This one is nothing new, a rectangular cross-section, okay? And the moment we apply here has an angle theta with respect to z. So it means arbitrary direction. You can apply any theta in this case. So what we will have? First step, y and z, because all of them are all symmetric axes, so they all belong to principal axis. As we mentioned in the previous example, after we know they are principal axis, our moment can decompose into two parts along them. One is my, the other is mz. This is the result of mz. This is my. Just times cosine theta and sine theta for each of them. And then, because each moment corresponding to different axes as a arm, so y and z for each cases, and the iz and iy are not the same. The definition of iz, because the direction, moment direction is here, so we got bh cubed. B is this width, b. Let me mention this correctly. And this is h. So this one, based on the direction of moment, iz should be bh cubed over 12. For iy, the direction just exchange, hb cubed for so-called iy, and it's used for so-called my. Okay, my, iy, z is the distance of thickness, and for iy is determined like hb cubed. This one is bh cubed for the other case. Then after we know all of them, here you will see a minus sign for mz and positive sign for my. Why? For mz, okay, if you consider the direction of y, positive sign would be this portion, the upper portion of this beam. And you will find that based on the direction of moment mz, we apply compressive stress on the upper part and tensile stress on the lower part. That's why we add minus sign for positive z, mz, and positive y. That's the reason we determine the sign for each equation. The other one, my should get so-called along the direction of z, positive Z is on the left-hand side. And we find that we get tensile stress over there, so we have positive sign in our equation, okay? And then we summarize them together, we determine the stress on overall cross-section, just like this one. This result is coming from the stress for MZ and the stress for MY. After we summarize them together, you will find that the distribution looks quite complex, and the zero stress can consist or give you the direction of NA, neutral axis. That is determined by all the zero stress together. Okay, and these four equations is the way we determine or we calculate so-called the maximum stress at four corners, or these typical stresses, important stress at the four corners. Here's the way we go through the process and derive the orientation of neutral axis. As we know, this is the stress function for MY and MZ together. MZ is equals to M cosine theta, MY is equals to M sine theta. We substitute them back to the equation, and we said, where can we determine our neutral axis? It's quite easy, because when the stress equals to 0, then that is the location of your neutral axis. So we give sigma equal to 0 for this equation, then we know that this term should be equal to the other term. This is the equation we have, okay? Based on the neutral axis definition, sigma should be 0. Then next one, once we have this one, we take y on one side, z on the other side, the remaining parameters together on the right hand side. And then after that, we put mz by m cosine theta, m over here, mz as cosine theta, my as a sine theta. All right. Then these terms give us a tangent theta. The remaining component would be iz, iy over here, and z is here. When you shift z to the other side, you get tangent alpha. This is the angle, tangent alpha. Y over z is the orientation or the angle of your neutral axis. Okay, and it's equals to what? It equals two portions, the product of two portions. Tangent theta is the loading angle. Okay, loading angle, the angle of your moment. The iz and iy are determined by your geometry, because they all come from, like for example, for this case, the combination of b and h. Different value calculated by different, give you different ratio of iz and iy. So neutral axis is determined by geometry plus your loading angle. For your principal axis, you totally determined by your cross-section shape, so it's determined by your geometry. Okay, so that's the difference between two important axes. Principal axis determined by cross-section shape, neutral axis determined by two contribution. One come from geometry part, is iz-iy ratio, and the other part would be loading angle theta. That's all we have for this important feature. Here's one example. Let us try to practice what we have learned in previous slides. Here's the cross-section. A rectangular one, the width would be 0.2, the length would be, or the thickness would be 0.4. And the axis of the longitudinal axis, would be x, and you'll have y and z along these two directions. And after that, we apply a bending moment m along the angle of 3, 4, 5, these special right angle. Okay, and this moment we try to see the normal stress developed at each corner, B, C, D, E, and also the orientation of alpha, the orientation of NA, okay, neutral axis. So before we go through all the detail, we first find the principal axis first. This one can be determined as two principal axes, y and z. Okay, so this is the first one. Principal axis, y, z should be determined first. After that, we know that we can use these two principal axes and decompose our moment my, mz. That is another part, my, mz. And then iy, iz can be given. After we know all these parameters, this equation can be applied by substitute the yz, mz, iz, my, iy over there. And then we calculate sigma b, c, d, e at four corners and get these local maximum value, okay, at each corner. And you will find that two of them are the same with a different sign. One is positive, the other is negative, similar to the other corner, okay? So that's the condition we have in this problem. After that, we need to determine our NA. How to determine that? One is determine this Z for the distance from B to C and try to find the 0 point along that boundary. That is one way we can have. That's the problem. The location of Z of NA you can establish by proportional. Just try to see the proportion of the stress distribution and you will find the location of Z. Here's the process. The maximum on one end, the other end, and the total length would be 0.2. This Z would be the ratio between them. So after that, we get Z as 0.0625 meter. Okay, in the same manner, you can get the same distance in opposite side of these beam. Okay, so after we know these, we still can use the equation alpha. Tangent alpha equals to iz over iy times tangent theta. Tangent theta, we have known that this theta value would be this value, minus 53.1 or 43. Okay. And somebody said if you use positive sign, that would be positive 306.9 degree. Okay. Either way, you can substitute into tangent theta. And iz, iy you can substitute together. Then after that, you get alpha is minus 79.4. Based on this direction, this is the theta of the moment, and this is the theta or alpha for NA. And this is 1. You will find that this NA really do not along any direction of them. It's just in the middle of y and moment n. Okay, very special.